Let's jump right into this explainer on the AWS Lambda Masterclass. We're looking at the journey from the monolith to an event-driven core. Imagine completely leaving behind the headache of traditional server management. Instead, we're stepping into this beautiful, dynamic world where your code literally only exists in the exact moments it's needed. It's a fundamental shift from static, always-on architecture to a completely serverless reality. The contrast here is, well, it's pretty stark. Think about the classic monolith. We've all dealt with the dreaded 3 a.m. problem, right? Your server's CPU is just sitting there at, maybe a 1% utilization rate, but your enterprise is still paying for 100% capacity. It's built on permanent hardware allocation, and honestly, it's inherently wasteful. But then, on the flip side, we have what senior architects are building today, the Ephemeral Matrix. In this model, applications physically cease to exist when nobody's using them. They just vanish. Then, they burst back into existence to handle massive traffic spikes. You're paying strictly for the exact milliseconds of execution. Zero waste. It's pretty amazing. To really picture this, think of your traditional EC2 servers like a permanent buffet restaurant. You've got to rent the building, hire the staff full-time, and keep the food warm 24 hours a day. And if 0 customers walk through the door, you eat 100% of that financial waste. AWS Lambda, though, is entirely like a vending machine. It just sits there in the dark, consuming 0 power, costing you absolutely nothing. But the exact millisecond an event occurs, bam, it powers on, mixes the ingredients for that one specific request, charges you a tiny fraction of a cent, and then instantly powers off again. You aren't really running applications anymore, you know? You're running functions. Now, to actually achieve that vending machine efficiency, an architecture has to pass a pretty strict litmus test. There are 4 true serverless tenets. First up, no infrastructure management. You are never picking an instance type or SSHing into a box, period. Second, you need automated inherent scaling, going from 0 to thousands in literally milliseconds. Third is pay-for-value billing, which is tied strictly to the compute time you actually consume down to the millisecond. And the fourth, the absolute ultimate requirement. It has to scale to 0. If there's no traffic, your bill is exactly $0. Just wrapping legacy binaries in Docker containers and running them on ECS nodes, that completely fails this test, because it doesn't eliminate those underlying idle compute costs. So, how do they actually pull off this instantaneous scaling at the hardware level? Well, AWS relies on Firecracker microVMs running on the Nitro Hypervisor. Unlike heavy, clunky traditional virtual machines, these things are incredibly lightweight. I mean, they're specifically designed for sub-second initialization. That's what makes that instant scaling possible. The hypervisor dynamically injects your specific runtime and function code the very moment an event happens. And the best part, it does all this while providing absolute, strict hardware-level isolation. You get total security even though you're operating inside this massive multi-tenant environment. Let's actually track the exact lifespan of one of these ephemeral compute nodes. It happens in 3 distinct phases. First, we have the init phase. A lot of folks call this the initialization penalty. This is where AWS boots the runtime and loads your code. Next up is the invoke phase. This is the actual execution of your business logic. And crucially, this is the only part where you're actually build based on memory and milliseconds. Finally, there's the shutdown phase, where the environment basically gets frozen in memory. Now, if another request comes in right away, you get what we call a warm start, which entirely bypasses that init phase. But if too much time passes, the container is silently destroyed. And that means your next request is going to trigger a cold start. You know, how you actually trigger these functions completely changes your architecture. With a synchronous trigger, a user makes a request through something like API Gateway and then just sits there, waiting for a direct response. It's an easy migration path, sure, but you're literally paying for wait time. The real magic of serverless is found in asynchronous triggers. This is the fire and forget model. Imagine uploading a file to S3 or publishing an event to EventBridge or SNS. That triggers massive parallel execution that is completely decoupled from the user. One single message could concurrently trigger 10 different Lambda functions to instantly process data in the background. It's incredibly powerful. When we apply this mindset to queues and streams, we get to eliminate a massive legacy anti-pattern, scheduled polling. Historically, servers wasted so many compute cycles just checking empty queues every 5 minutes. The serverless pattern fixes this so beautifully. AWS essentially runs a native radar sweep. If your SQS queue suddenly gets slammed with 100,000 messages, the Lambda service naturally detects it. It autonomously scales up concurrent functions to drain that queue safely without you ever writing a single polling script. The exact same thing applies for DynamoDB streams, triggering real-time replication the very millisecond a record is updated. Okay, but this brings us to a really critical architectural bottleneck. Relational databases are, at the end of the day, fragile physical storage components. If you have infinite, instantly scaling Lambda functions opening synchronous connections to, say, a PostgreSQL database, you are creating a catastrophic synchronous anti-pattern. You will violently exhaust your database connections, it's going to crash. The enterprise fix here is elegant decoupling. You just insert an SQS or event bridge buffer. The database fires its payload asynchronously into this buffer, instantly commits its local transaction, and never once has to wait on external compute. But what if you absolutely must talk directly to that legacy database? Well, architects can manipulate the physics of the cloud to protect those downstream systems using something called reserved concurrency. So your AWS account has a soft limit of 1,000 concurrent executions. If you expose a Lambda function to the public, a huge traffic spike could just obliterate your database. To prevent that, you carve out a strict reserved limit, let's say 50, and assign it to that specific function. It can now literally never exceed 50 simultaneous executions. If request number 51 comes in, Lambda violently throttles it, returning a 429 error. It deliberately sacrifices the request to save your SQL database from crashing. And of course, the code itself has had to evolve right alongside this infrastructure. Tier 1 was basically the naive microservice Death Star. Developers would just cram an entire monolithic web application into one single function. This led to massive payload sizes and horrible, 8-second cold starts. Then came Tier 2, the service-oriented cut, which assigned one function per API method. It was better, but still tightly coupled to synchronous wait times. Tier 3 is where we want to be, the serverless core. This is truly decoupled, asynchronous, event-driven architecture. Zero shared state, extreme granularity, and processing queues and streams completely detached from user wait times. Now, for a lot of enterprises, trying to adopt that Tier 3 core hit a pretty major roadblock. And that roadblock is the initialization penalty for statically typed heavyweight languages. If you're writing in C#.NET or Java, booting up that runtime environment and loading all those massive dependency trees, it takes time. The init phase alone can take 2 to 5 seconds. And if you have a synchronous web application relying on an API gateway, a 5-second delay for the very first user hitting the system, that is a catastrophic user experience. No one wants to wait that long. So the initial solution to this was essentially a brute force financial hack called provisioned concurrency. As a deliberate trade-off, you could pay AWS a continuous hourly rate to pre-initialize a set number of environments and just keep them permanently warm. And it works. It successfully ensures double-digit millisecond latency by completely eliminating cold starts. But there is a huge catch here. This explicitly breaks the scale to zero tenet we talked about earlier. You're right back to paying for idle compute, effectively turning your perfectly good vending machine back into a buffet. But recently, AWS solved this so elegantly by essentially rewriting the physics of the execution environment with Lambda SnapStart. Instead of paying to keep environments warm, AWS does all the heavy lifting at publish time. It boots your runtime, runs the initialization logic, and takes a fully encrypted snapshot of the microVM's exact memory and disk state. So when 1,000 users hit your API all at once, AWS just instantly restores 1,000 copies of that pre-initialized memory snapshot. This drops cold starts from seconds down to sub 200 milliseconds. And the crazy part, you don't have to change a single line of your code to use it. When we talk about the enterprise, security usually demands private networking. By default, Lambda runs in an AWS-managed virtual private cloud, which means it can't natively reach your private corporate databases. To securely place these ephemeral constructs safely inside the corporate firewall, Lambda creates an elastic network interface, or an ENI, that maps directly to your enterprise private subnets. This gives you total database isolation. Your RDS instances can live completely offline, totally inaccessible from the public internet, while your Lambda functions can safely interact with them from the inside. Living in this ephemeral world does mean you have to design within some incredibly strict environmental constraints. For example, there is a hard, unchangeable execution limit of exactly 15 minutes. At 15 minutes and 1 second, the hypervisor will violently terminate your process. On top of that, you really only have one dial to tune: memory. As you increase the memory, AWS proportionally increases your virtual CPU and network bandwidth. And remember, because billing is tracked in absolute 1 millisecond increments, unoptimized algorithms literally translate directly into a higher monthly bill. In serverless, code efficiency directly equals financial efficiency. Because of this incredibly ephemeral nature, your design has to be entirely stateless. We really have to embrace this idea of digital amnesia to achieve infinite scale.
Think about legacy monoliths that store user session data in local server RAM. They instantly break the moment a second server is added behind a load balancer. The serverless reality demands that every single function execution is treated as a complete blank slate. It has absolutely no memory of previous interactions. Any durable state, session data, or persistence has to be forcefully pushed out to decoupled storage layers, like DynamoDB or S3. So that begs the question, how on earth do we handle long-running workflows that break that 15-minute limit? Historically, we'd rely on AWS step functions for complex orchestration, but there is a massive shift coming with the 2026 game changer, Lambda Durable Functions. Very soon, standard functions will be able to explicitly suspend their own execution. A function will be able to just pause for up to an entire year, waiting for an external webhook or for a human to click approve. And while it's paused, your idle compute billing is exactly $0. When the trigger finally happens, Lambda wakes up, natively replays its exact state, and picks up right where it left off. This level of granularity inherently revolutionizes your security posture too. In a monolith, if a server gets breached, it exposes the whole environment because that server's IAM role has to have permissions for everything the application touches. Serverless adopts least privilege execution roles. Every single Lambda function is assigned its own dedicated microscoped IAM role. Your process payment function can only access the billing table. Your resize image function can only write to one specific S3 bucket. If a single function is somehow compromised, it yields absolutely zero lateral movement. It strictly contains the blast radius. And all of these individual concepts we've talked about, they ultimately combine to form the ultimate serverless core. It's the ephemeral matrix, running in perfect harmony. You can trace this elegant flow from the API gateway routing requests to Event Bridge acting as your enterprise bus, triggering this inherently scalable ephemeral compute layer that effortlessly interacts with persistent state in DynamoDB. Developer velocity is maximized, your infrastructure is reduced to just mere lines of code, and it's fault-tolerant by design. It truly represents the absolute pinnacle of modern enterprise engineering. Which leaves us with one vital question to wrap up this explainer. Looking at your current enterprise architecture today, are you still paying to keep the buffet warm,